Hello, everyone. Welcome to this session of ICM, where we'll hear about the mathematics of hiding secrets in software. I'm Salil Vadan, a theoretical computer scientist at Harvard. And as our speakers for this session, we have two experts in the foundations of cryptography and security. Rachel Lynn, who's an associate professor at the Allen School of Computer Science and Engineering at the University of Washington. She has won an NSF Career Award, a Hellman Fellowship, a J.P. Morgan Faculty Award, a Microsoft Research PhD Fellowship, as well as numerous Best Paper Awards. And our other speaker is Amit Sahai, who is the Symantec Chair Professor of Computer Science at UCLA and the Director of the Center for Encrypted Functionalities, as well as a Simons Investigator, a Fellow of the ACM, a Fellow of the IACR, and a Fellow of the Royal Society of Arts and Advisor to the Prison Mathematics Project. The talk will be recorded. You can use Discord channel 14 for section 14, the mathematics of computer science, to ask questions during the talk, and the speakers will try to answer. And if we have a couple of minutes at the end, I will read those questions, any remaining questions live to them. Because of the time zone, they likely won't be available after the talk to answer questions on Discord, but possibly could check in the next day or two. All right, let's begin.
Hi, everyone. My name is Rachel. I'm very happy to be invited to tell you about our latest work.
And my name is Amit Sahai, and it's truly an honor to be here to speak at this special sectional lecture at ICM. And what we will be talking about is the mathematics of a fascinating and seemingly impossible goal, that of hiding secrets within working software. And this is joint work with our wonderful collaborator, Aayush Jain, who's at CMU. So before we get into that, let's take a step back and just think about what this problem means in a little more personal way. So suppose that it was you who wanted to keep a secret. But unfortunately for you, there's an adversary that has captured your entire brain and knows everything about your brain, knows where every neuron is, knows exactly what's going on. And unfortunately for you, this adversary can read and tamper with every single neuron in your brain. And in fact, it can do so while you are thinking about the secret that you want to protect. Now, I hope this never happens to you. It doesn't seem to happen to too many people, thank goodness. But imagine how difficult that would be, how difficult it would be to keep a secret from a mind-reading adversary. Unfortunately, the computational analog of this scenario is all too common. The analog of your brain is a computer program, right? And a computer program can be captured by an adversary very easily. In fact, in many cases, we simply give out our computer programs. We sell them, and the adversary can, of course, look at the code because he's bought the program from us. So what we want to do is we want to see, is there a way to have this computer program keep a secret even when it has been entirely disclosed to the adversary? And we're really thinking about a situation where there's no trusted hardware to keep some secret for us. There's no interaction with some external server who can keep some secret for us. Nothing is secret whatsoever about the workings of this brain, the workings of this program. It runs on a public computer that is known to everyone. The adversary knows everything about it. Okay. And furthermore, the program itself is just an ordinary program with ordinary inputs and ordinary outputs. It doesn't have encrypted inputs and produce encrypted outputs, just ordinary inputs and outputs. And again, this is a very widespread, long-standing problem in computer science. It dates back at least to 1976. The classic work of Diffie and Hellman introduced this idea of a one-way compiler that could somehow transform a program into an equivalent form, but which hides the secrets that were present in the original program. And now that paper discusses informally, but didn't actually define this notion precisely. And there's some good reason for that. Defining obfuscation, this way of mungling up the workings of a computer program, is not completely straightforward. And let me illustrate that right now. So first of all, we have to think, what programs even allow for secrets to exist? Something like a hello world program obviously doesn't have any secrets. It just prints hello world and there's nothing else to it. But even programs like the one shown here, where the program seems to have a secret, has some constant secret s built into it. But what the program does is it just takes the input x, compares it with s, and if the input is smaller, it outputs 1, otherwise it outputs 0. So here, the problem is that even though the program may want to keep a secret, just the functionality of the program causes it to reveal its secret. And what do I mean? If any program equivalent to this program P is revealed to an adversary, then the adversary can simply talk back and forth with the program, provide some inputs, see what the output is, and use binary search and learn what the constant s is, right? Just in a straightforward way and an efficient way. And this indeed presents a fundamental barrier for us, that any program whose secret can be learned efficiently with input-output queries, certainly there's no hope of hiding that secret, right? And it also, however, gives rise to an interesting idea. So again, there's a clear barrier that a secret must at least be unlearnable from a bounded number of queries to the program. Okay, here I want to take this opportunity to point out that we are always dealing with computationally bounded adversaries whose running time is polynomial or in some way asymptotically bounded. And because it's bounded, that means the adversary can only, for example, interact with the program a bounded number of times. And that's absolutely crucial. We're not thinking about learnability with an unlimited number of queries to the program, but from a bounded number of queries to the program. But could it be that this is our only barrier? Could we define our notion of obfuscation as transforming a program into an equivalent program, which is as good as a virtual black box that just sort of hides everything but the input-output behavior of the program? This is a very natural idea, and it was considered in joint work with several of my co-authors back in 2001 as the virtual black box definition. But unfortunately, we formalized it and then immediately ruled it out. I won't go into the details of the formalization, but I will tell you roughly how we ruled it out. Very roughly, what we did was we construct this admittedly very contrived program, P of x, which works in the following way. It takes some input x, and it checks if the input x is, roughly speaking, a program equivalent to P. If it is, then it outputs the secret s, and otherwise just outputs 0. Now, why is this a good counterexample? Because if you only had black box access to this program, what are the chances that you'd be able to guess any program that's equivalent to P? It's exponentially small, very, very small, right, that you would be able to guess it. Therefore, if you only have interaction with this program, it's just going to output 0 all the time, right? However, if you gave me any obfuscated version of the program P, you could just feed it to itself and it will be guaranteed to output the secret s. So in this way, we have this very contrived counterexample. And even though it's a contrived scenario, and in fact, we only have negative results for such contrived scenarios, this definition has a counterexample. And we don't want to build our theory of mathematical obfuscation on a definition that has counterexamples. So we want a definition that can be sort of more pristine in terms of its applicability. In the same paper, we did consider a weaker definition, which will be the main definition that we will be talking to you about today. And that definition is called indistinguishability obfuscation. So let me zoom in a little bit more and give you a few more details of what exactly this object is, this IO object, okay? So first of all, we're going to be obfuscating programs P, as shown here. We're going to represent a program without loss of generality as an arithmetic circuit over the Boolean field, over the field of 2 elements, F2, which takes as input some n tuple over the field and outputs a single field element. Okay, this is without loss of generality. This can be generalized to Turing machines in fairly natural ways. Okay, the IO compiler, the IO program that takes as input this program and outputs another program, is a randomized polynomial time algorithm. And the randomness is absolutely crucial here. That randomness is private. It is tossed during the obfuscation process, but not revealed to the adversary. The only thing that's revealed to the adversary and to the world is the program that is output by the IO compiler, which we denoted p tilde here. And this output program has to be equivalent to the input program. That is, for all inputs x in f2 to the n, p of x equals p tilde of x. Okay, these are the basics of a sort of obfuscating compiler. Now, the security property considers now two programs, p0 and p1, which are equivalent and the same size, meaning that they're the same size, and for all x in f2 to the n, p0 of x equals p1 of x. Okay, and just to give you an example, for example, p0 could be this polynomial a plus b times c plus d minus ac, whereas p1 could be the multilinear form of that, ad plus bc plus bd. Of course, they're equivalent. They're computing the same underlying polynomial, but in different ways. Okay, and then these are both passed through the IO transform. And what the security property states is that the resulting distribution of programs, p0 tilde and p1 tilde, are hard to distinguish for any efficient adversary. Okay, and we can define that very precisely as written here. I'm not going to go into the details of this. You can pause and look at it later if you'd like. But again, what it's saying is that every polynomial time adversary can't distinguish between IO of P0 and IO of P1, except with negligible probability. Okay, and what does this mean sort of more intuitively? What it means is that IO hides any implementation differences that exist between P0 and P1. In other words, what we learn is the functionality, but not the implementation choices that were made to implement that functionality. In that way, IO can be seen as a sort of efficient pseudo-canonicalizer of programs, since a canonical form would have this property. Of course, we don't expect efficient canonical forms to exist for programs, but in this way, we want to get something close, a pseudo-canonicalizer. So with that out of the way, let me switch it over to Rachel, who will tell you more about why IO is interesting.
Yes. So given that we now have a good definition that doesn't have any counterexamples, we ask the question, is it useful? It turns out that IO is extremely useful in enabling advanced cryptography. To give you an example, we can use IO to allow a processor to be able to process over encrypted data. The basic idea is to give the processor an obfuscated program which actually has the right secret key hard-coded inside. And the logic of the program, on input and encrypted data, will simply decrypt the data internally, do the right processing, and finally re-encrypt the data and output the re-encrypted ciphertext. This way, using very simple way of using IO already allows us to implement this very magical tool called fully homomorphic encryption. For those of you who are interested in it, please do not miss Craig Gentry's talk on Wednesday afternoon for more. The advantage of obfuscation is that it's very flexible. So we can slightly modify the logic of the obfuscated program to allow it to give out part of the processed data in the clear. This suddenly implements a different magical tool called functional encryption that we didn't know how to achieve without IO. And in fact, it turns out that making those simple ideas work isn't trivial because the IO security only holds when we have two implementations, different implementations of the same function. But it cannot be directly used to reason about a single implementation and whether they hide certain secrets. Nevertheless, fortunately, that the community has developed many novel techniques for using IO that can overcome the weak security guarantee. In fact, using these techniques, we have shown that IO is some kind of a master tool for cryptography. What I mean is that if we have IO and together with some very minimal hardness conjecture, such that NP is not included inside the BPP, then we can realize most known cryptographic goals. This would include classical cryptographic goals, such as one-way functions, public key encryption, etc. It also builds a connection to complexity theory, such as implying the hardness of finding Nash equilibrium. And furthermore, Furthermore, that I/O has taken us to build a host of new cryptographic goals, such as functional encryption, etc., that we didn't know how to achieve before and did not even think about trying to reach before. With all these applications, we are all excited. And so why don't we just go ahead and prove that I/O exists? It turns out, unfortunately, this is just not how cryptography works today. The state of affair is that we are far from proving even the existence of very simple cryptographic goal, like one-way function or public key encryption. In fact, even more basic hardness conjecture, like P not equal to NP, remains wide open, and this is a major barrier in our field. So instead, the cryptography has turned to aim at building tools based on certain well-studied hardness conjecture, such as the hardness of factoring, which states that factoring the products of very large primes will take super polynomial time. There's also other widely recognized conjectures, such as learning with errors, discrete logarithm, learning parity with noises. The bottom line is that in this approach, we really want to only rely on hardness conjectures that have been really carefully examined and thoroughly vetted through cryptanalysis. We also prefer those hard problems that has connection with other fields such as mathematics, complexity theory, information theory, etc., because they provide very precious tools for us to analyze those hard problems. So today, our goal is to build I/O from well-studied hardness conjectures. And in fact, starting from the first candidate proposal in 2013, there had been dozens of construction. Sorry about that. There has been dozens of construction using different approaches towards I/O. And up until recently, all those different proposals somehow rely one way or the other on newly conjectured hardness. And unfortunately, through subsequent cryptanalysis, many attacks have surfaced. However, all those works have built up a body of really useful technique and really paved the way to our two recent work that finally built I/O from three well-studied hardness assumptions. And they are first, learning parity with noises, shorthand as LPN, over large fields. And the second is assuming the existence of pseudo-random generator that has a local structure. And the third is that we assume a hard problem called decision linear is indeed hard on an algebraic object called bilinear map. We won't have time to go into details of each of those hardness conjectures. However, we will briefly mention each of them later in the talk. It's important to note that all these problems has had a long history of study and application in cryptography, and each of them has roots in information theory, complexity theory, number theory, and algebra. Now, the next question is, how is this theorem proving? So let me now turn the podium back to Amit to tell you about our high-level ideas. Amit.
All right. Thank you, Rachel. Let me take control again. So how can we prove this fascinating theorem? Well, let's first start by thinking about a simple straw man approach. So recall that the definition of I/O is that of a pseudo-canonicalizer, right? It's supposed to hide everything except hide all implementation differences that may exist for implementing some particular function. Well, then one very simple way for us to do that would be to simply write down the truth table of the function. In other words, just take our program P, evaluate it at all possible 2 to the n inputs over f2 to the n, and just write down all of the outputs, right? This is certainly a canonical form for our function over f2 to the n, and it achieves the definition of I/O, except for efficiency. Remember that I/O has to be an efficient transformation, whereas this transformation is clearly very inefficient. So what this shows, however, is that it really boils down to efficiency. We really want to somehow take this efficiency requirement and keep pushing on it until we achieve I/O. So in order for us to do that, let's first take a change in perspective, okay? Instead of thinking about this in terms of programs, let's think about this from the viewpoint of encryption. And what I mean is, suppose we had a way to encrypt our program using some special kind of leaky encryption, where normally we think of encryption as something that hides everything about the message being encrypted. Now, suppose that what we could do is we could encrypt our program P in such a way that the adversary or the user can actually learn certain specific functions of P. Okay, and what functions are we interested in? Well, we're interested in functions like these F alphas, where F alpha of P is simply equal to P of alpha, these evaluation functions, right? For all alpha and F2 to the n. If we could somehow encrypt our program in a way that allows the user to learn all these functions and learn nothing else, only learn the outputs of these functions, then this would indeed achieve the definition of I/O, right? Because it would again allow you to learn all of the input-output behavior of this function, and yet everything else about the program P is kept hidden, which means in particular all implementation differences are kept hidden, right? This special kind of encryption is called functional encryption, and Rachel briefly mentioned it already. And so we would like, if we could achieve this, then we would be able to achieve I/O. Now, what's a barrier here? Well, a key barrier is, well, there are two key barriers. One is about the size of the encryption. So for us to be able to do this, to have this achieve the definition of I/O, we would need the size of this encryption to be polynomial in the size of the original program P. That's a really tough goal. Thankfully, some wonderful previous work has made this goal a little bit easier. And what previous work has shown is that, in fact, if we can simply reduce the size of the encryption when compared to the truth table by just some small polynomial factor. In this case, for example, we know that the truth table size is 2 to the n. If we could make the size of the encryption just 2 to the n to the power 1 minus epsilon for any constant epsilon greater than 0, then in fact, we're able to recursively apply this functional encryption idea to achieve our final goal and actually achieve I/O. And this is a really wonderful tool that we're going to be able to use. So let's now aim for that. Let's try to aim for this more modest efficiency goal that's stated here. That's good. That's going to help us. But there's still one other key problem, which is that when we look at these evaluation functions, F alpha of P equals P of alpha, these can be arbitrarily complicated, right? They contain at least as much complexity as the original program does. And we're unfortunately far from being able to handle these general cases, or we were far from being able to handle these general cases earlier. So now we want to think about how can we reduce this problem? How can we make this the complexity of these F alphas simpler so that we can somehow achieve our goal? Here, what we will do is we will first generalize slightly. Instead of simply encrypting our program P, we will encrypt our program P together with some randomness R, okay? And now our functions F alpha of P comma R, they don't simply output P of alpha. Instead, they output information that allows a user to reconstruct P of alpha and nothing more, okay? So in this way, we've slightly generalized our previous notion to allow for this reconstruction of the output. But this turns out to be a very useful generalization, okay? And in fact, what it lets us do is the following. First, we can use some classic work that dates all the way back to Andy Yao's work from 1986 to be able to reduce the complexity of these F alphas very considerably. So we can reduce the complexity of F alpha all the way down to a constant degree polynomial. Unfortunately, that constant degree will be fairly large constant, but still a constant degree polynomial that will also have constant locality, okay? And we're able to do this by furthermore assuming pseudorandom generators that are computable by constant locality polynomials. This is a long-standing direction and conjecture in cryptography that dates at least as far back as Goldrake's proposal from 2000 and has been extensively studied. Okay, so we've reduced the goal to just being able to handle constant degree, constant locality functions f. And on the other hand, on the constructive side, using elliptic curves and the efficient computation of the Weyl pairing due to Miller, we can actually construct these kinds of special encryption schemes for functions f alpha that are degree 2, in P and R, these things that we want to keep secret. Okay. In fact, they can be degree 2, the function can be degree 2 in P and R, but can also be an arbitrary constant degree in additional public information. That's a feature that will turn out to be very useful, as you will see in just a moment. And this is based on a vast literature on pairing-based cryptography that makes use of elliptic curves in this beautiful way. And it's, on the other hand, we are very much stuck at degree 2, or we were very much stuck at degree 2 earlier, because of the fact that the pairing, the Weyl pairing, is a pairing. It is a sort of inherently a degree 2 object. So in order for us to finally achieve our goal, we have this sort of fundamental challenge, which is to reconcile these two problems. That on the one hand, if we could only achieve functions that have constant degree greater than 2, then we would be done, we would achieve IO, whereas the only tool that we have is something that allows us to achieve degree 2. So how can we reconcile these things? And this is what Rachel will now tell us about to take us home in the final portion of this talk. Before I hand it off to Rachel, let me just restate the problem a little bit. So here is, our goal that I just presented, the special encryption that allows us to learn these functions f alpha that are local. They're constant, local, constant degree functions. And we wanted the size of the encryption to be polynomially smaller than the truth table, than the output here that we want to be able to obtain. So we're going to abstract that out a little bit and just think about a case where we have to encrypt just some input x, and we have a function f, which is local. It produces some output y, and we want the size of the encryption then to just be polynomially smaller than this output y. Okay. And again, the main challenge is that we only have the sort of special encryption for degree 2 polynomials, whereas these polynomials f will be local and constant degree for general constants. So with that, let me turn it back over to Rachel.
Yes, thank you, Amit. So exactly, this is now our goal. Let's think for a second that if I want to obtain the final output y, however, somehow hide all other information about x that isn't conveyed by y, then it is necessary that we actually hide every intermediate computation value, because every intermediate computation value may leak additional information about x that is not present in y. This requires us to hide a constant degree computation, but we only know how to hide a degree 2 computation. So our idea is to actually transform the computation in some way so that only a degree 2 step needs to be hidden and other parts can just be computed publicly. More specifically, this would involve us to first transform the input x into 2 parts called Q and S, where the Q part is public and the S part is secret. Next, we want to transform the original local function f into this new form, which will only have constant degree on the public input Q and allowing degree 2 in the secret input S. In more detail, this we call as our special polynomials, where every output element yk can be expressed as a sum of quadratic monomials over the secret input S, and the coefficient may actually depend on the public input Q, and the dependency can have constant degree. And in order to make sure that the final encoding of X that we get is actually efficient, we require the public and secret input together has total length that is much shorter than the output length, say 0.99. In order to achieve this goal, we will use the hard problem, learning parity with noise, over a large field FP. So let me tell you about it. This relates to decoding random linear codes. So given a randomly chosen coefficient matrix, and together with C, which is the multiplication of this matrix A with a secret and randomly chosen vector S prime, we know that using Gaussian elimination, we can efficiently solve for S prime. LPN states that this problem suddenly becomes hard when we just corrupt C a little bit using very sparse errors. Here, the sparse error vector, each of the coordinates of it is sampled independently. And in fact, most of the coordinates are simply just 0, with only very small inverse polynomial probability, 1 over k to the delta, where k is the dimension of the secret, and delta is a constant between 0 and 1. Let's think about just delta equals to 0.2. With only this very small probability, a coordinate is non-zero. And when it is non-zero, it is chosen completely randomly from the field FP. Now, once C is corrupted with this very sparse error, it becomes hard to solve for S prime. In fact, it is further shown that this implies that C will appear hard to distinguish from simply a random vector R. This is a problem that has had a long history of study in coding theory, and so far the best known algorithm requires sub-exponential time in order to solve for S prime given C. So using LPN, we can create a very simple encryption scheme that allows us to hide the input X. How? Simply add X to the corrupted C part. The fact that A times S prime plus E is hard to tell apart from a truly random vector ensures that the input vector X is hidden. So we can view the S prime as a secret key and each of the row as a ciphertext. A nice property of this way of encrypting is that it has very simple decryption. In fact, decryption is just an inner product between a row, the ciphertext AI, CI, together with the vector minus S prime, 1, which is our new secret S. With just in the product, we can already get the encrypted input element, however, potentially corrupted with some very small polynomial, inverse polynomial probability. This approximate linear decryption structure implies that we can somehow homomorphically evaluate a constant degree polynomial. Let's think about evaluating this constant degree polynomial on the right-hand side over multiple xi plus ei. What we would get is the output of the function evaluated on the corrupted input vector x. And this can be rewritten as actually the exact output plus some error vector r. On the left-hand side, if we evaluate f on a collection of inner products, it can actually be equivalently viewed as first doing some constant degree D computation on the ciphertext alone to obtain what we call an output ciphertext CF. And when we tensor the secret vector S with itself D times, using this vector to multiply with CF were equal to the left-hand side when being evaluated with F. So furthermore, we observe that if the function f is in fact local, if the function f is in fact local, then the error in the final output is sparse. To see this, note that a local function means every output element depends only on a small constant number of input elements. Since the input elements are only corrupted with very, very sparse errors with probability 1 over k to the 0.2, and every output element is intact and corrupted only if one of its neighbor is corrupted, hence the probability that it's corrupted is only a constant factor higher, still very, very sparse. putting all this together in summary, we can homomorphically evaluate a local function f on LPN encryption, and the output ciphertext, when decrypted, give us the right output corrupted with some sparse error. Note that it is actually very important that we must make sure the error vector keeps hidden, because otherwise we can just solve for a linear equation and find S and all security is jeopardized. With this homomorphic evaluation in mind, we can now come to transforming a local function into those special polynomials. First, let's think about how to encode the input X. We're going to hide the input X inside the public input Q by encrypting it using LPN. And the homomorphic evaluation we just talked about means that we can actually homomorphically evaluate this local function f on this LPN ciphertext and obtain an output ciphertext C of f that encrypts the output y. Now, to recover y, we simply just want to decrypt somehow in degree 2. And this can be done by including the tensored version of the secret vector. And then in the secret computation, multiply CF with the tensored secret vector, and that should recover almost output y, except it's corrupted by the error. Unfortunately, as we mentioned just now, that it's extremely important to hide the error vector, otherwise it will jeopardize security. One simple idea is that we can remove the error by including it in the secret part of the secret input, and then simply subtract it off. This would allow us to recover the exact output y. The problem with this approach is that the error vector is actually pretty long. It is as long as the output. If we include it in the secret input, we will not be able to achieve the efficiency level that we want, which is the Q and S part are sublinear in the length of the output y. In order to overcome this, our idea is that the error vector is actually very sparse. So maybe there's a way that we can compress its size to be much smaller. And this brings us to an algorithmic task, the compression task, which we want is to design two algorithms, compress and expand. The compress algorithm, given as input a very sparse error vector of length m, will produce the compressed version u, v of length much shorter. And the expand algorithm, given the compressed version, recovers back the error vector with the constraint that it can only use simple degree 2 computation. To illustrate the idea behind compression, let's start with a very simple case where the error vector is so sparse that it contains only a single non-zero error, w. It is somewhere inside this very long vector. Our idea is that we can somehow convert this error vector into a square root of m by square root of m matrix m. Any conversion is fine as long as it forms a bijection. And now this single non-zero error element is going to land somewhere in the matrix. And everywhere else in the matrix, it has entry 0. So this means that this is an extremely low rank matrix. In fact, just rank 1. And it can be decomposed into the product of two vectors, u and v, each just of length square root of m. So here we go, that these two vectors are going to be the compressed version. They are indeed much shorter than m, and the expansion is extremely simple. Just multiply them together, which uses only degree 2. This very simple idea can be generalized to tolerate more non-zero elements inside the error vector, however, only up to square root of m. But in our actual case, we would like to handle denser error vectors that the error rate is potentially, say, constant over k to the 0.2. In order to handle this case, we're going to think about dividing this matrix M into bins of dimension k to the 0.1 by k to the 0.1. And we will convert the error vector into this matrix in a way that ensures that no bin is too clustered. And in other words, there are at most, say, logarithmic number of non-zero errors inside each of the tiny little bin, each tiny square. Once this is true, we can use the same idea before to compress each of the bin and include all the compressed version in together as the final compressed version. Expansion works just as before and has only degree 2. Now, with compression, we can now complete our transformation. Instead of including the error vector directly in the secret input, we're now going to first compress it down into U and V and include that. During the decryption process, we will first expand it over back the error vector and subtract it off, and that will give us the exact output Y. Let's verify that all conditions are satisfied. The computation over the public input indeed has only constant degree, in fact, the same degree as the function f. The secret computation has degree 2, and thanks to the compression, now both the public and secret input has length much shorter than the output Y. This concludes our idea of bridging the gap between hiding a local constant degree function and hiding only degree 2 polynomials. And this enables us to build indistinguishability obfuscation, this very, very powerful tool based on 3 well-studied assumptions. And looking forward, there are many questions that remain open and they're very, very interesting, such as, can we reduce the number of hardness conjectures that are used? Can we build a more efficient indistinguishability obfuscation? Can we achieve stronger post-quantum security? And I hope that you're interested in these questions too. And thank you very much for your attention.
Thank you very much, everyone. And with that, we will conclude our talk.
Thank you, Rachel and Amit, for the great talk. We have just a couple of minutes left. So if anyone listening wants to quickly type a question into Discord, the channel for section 14, I will read it out to Amit and Rachel. While we are waiting, let me ask a question. Of the 3 assumptions that you're making use of, do you have intuition? Which one is doing the most work, is maybe the most essential? Or alternatively, are there other candidate assumptions out there that you think might be suitable for constructing I/O?
Right, that's a great question. And I wish we had good answers to that. If we would, then we would have published about it. So right now, unfortunately, all 3 assumptions seem to be playing a pretty crucial role in the ways that we sort of laid out in the talk. I would like to believe that the LPN is doing the most essential work, and hope that maybe we could eventually get rid of the other 2 assumptions, or maybe replace them with LWE or something like that. But we don't have any actual idea of how to do that. There are also alternative approaches that other people have looked at that may give additional ways to get simpler assumptions. And Rachel, would you like to add anything to that?
Yeah, so somehow in my mind that right now, one assumption plays a very important role, which is a bilinear map. And they plays the role of the compression, because Amit talked about in our talk is that the game is how can we compress, that we can trivially get an obfuscation which is as large as the truth table, which in fact is the truth table itself. And the important thing is whether we can have a representation that doesn't contain more information, but yet is smaller than the truth table. And so for looking at all 3 assumptions, the assumption that is giving us a minimum of this flavor is the bilinear map, and we don't have any other assumption that can be used to replace it. So one of the approach that people have been trying, in fact, is to replace it using LWE, learning with errors, because it enables fully homomorphic encryption, in a very direct way without using I/O. And this is something that potentially can give us compression, but so far we don't know how to do it. We are still at the stage of formulating new questions.
Great, fascinating. Thanks so much. I think we are out of time. So thank you again for the talk and for waking up so early for this session.
Thank you.
Thank you, Celia.
Hello, can you hear me?